Hey everyone, welcome back to Windows Seat Studies. I hope you all are doing well. So, we were discussing neurobiology, in which we were discussing about the electrical properties of neuronal membrane. So, in last class, we discussed about resting membrane potential, that the potential that a neuron has, the membrane of a nerve cell has when it is at rest, when no stimuli is being generated, okay, or when no stimuli is being given to that cell. So, if in today's class we are going to learn about action potential, the transient and regenerative signal which is caused due to the changes in ion permeability across the membrane. So, whenever there is some stimulus, the permeability of the membrane will change to, like, the ion fluxes will be different from what they were when the cell was at rest, and this generates a signal which is regenerative and which is transient, which we call as action potential. So this action potential travels from, this action potential is the route of traveling the information from one part of the body to other part of the body. And that is why it is quite important thing to learn about. So we are going to learn about action potential, which is a transient and regenerative signal. And this is caused by changes in ion permeability. Okay, so in last class we learned about resting membrane potential, which is which is maintained or which is generated due to the non-equilibrium condition, the non-equilibrium gradients of the ions across the membrane. Okay, and the maintenance of the driving force, maintenance of the charge separation is done passively as well as actively. So that is maintained due to the leaky ion channels, the potassium leak channels that are present on the membrane, as well as the fewer, like the compared to the potassium ion channels, the sodium leaky channels are very less, but yeah, they are there. So the membrane is selectively permeable to potassium ions, but it is somewhat permeable to sodium as well as chloride ions. The chloride ion flux depends on the situation. So, in the resting membrane potential, in the last lecture, we learned that the equilibrium potential that for a certain ion that can be calculated by Nernst equation. Okay, so Nernst equation tells us about the equilibrium potential, and at the rest, when there's no stimulus arriving on this at the membrane, the equilibrium potential of potassium ions, that is some equal to the membrane potential. So the membrane potential at rest is is nearly equal to the equilibrium potential of potassium ions. It is not exactly equal because there are some sodium leak ion channels which are going to do the transport of the sodium ions from outside the cell to inside the cell. So that this is what we learned in the last class. So Nernst equation tells us about the equilibrium potential of certain ion. Here we are measuring the equilibrium potential of potassium ions because at the rest that is equal to the membrane potential here. So let me just erase this. So the equilibrium potential of potassium ion, it depends on the room temperature, the temperature and the gas constant. So ZF, F is the F is a constant here as well. So then it is RT by NF into Ln of the concentration of that ion, so concentration of potassium ions outside the cell divided by potassium ions concentration inside the cell. So this is the equation where we when we put all of the values, all of the values of the constant, the R, F, and temperature. Here it is at room temperature, 25 degrees Celsius, and then when we put the value of our log pestin, so that 2.303. After putting all those values, it comes out to be 58 millivolt divided by Z log pestin Kn. So this is the summary that we learned in the last class. Okay, so and this is minus 75 millivolt at rest. So this differs. This has a range up from minus 60 to minus 90 millivolt is the resting membrane potential. Depends on the which nerve cell we are talking in that scenario. The action potential that is generated due to the changes in ion fluxes. So at the rest, the this membrane potential is, it is maintained due to sodium potassium ATPase. So sodium potassium pump does the active transport of the sodium and potassium ions, which helps us maintaining the concentration gradient of sodium ions and potassium ions. So usually at the rest scenario is something like this. So this is the plasma membrane of nerve cell, and this is the extracellular matrix, while this is the cytosolic part. Okay, so on the extracellular matrix, the concentration of sodium ions will be high and concentration of chloride ions will be high compared to what we have inside the cell. Okay, and inside the cell there will be higher concentration of potassium ions and a lot of anions which cannot leave this plasma membrane. So they cannot leave this cell because the plasma membrane is totally impermeable to anions, and that is why there is a negative charge build up on the inside of the cell while a positive charge builds up outside the cell. So this is the scenario at rest, when the cell is at rest. So when the stimulus arrives at the nerve cell, what happens is that the ion starts, the some ion channels open, and that starts the flux of the ion. So the charge separation which was at rest is either reduced or it is increased. So in normal scenario the charge separation is reduced. So the charge separation across the membrane is reduced, which results into depolarization of membrane. Okay, so the very first thing that happens is the depolarization of membrane. So what happens is that when stimulus arises, this opens the sodium voltage gated sodium ion channels. So it opens the voltage gated sodium ion channels. So after opening of voltage gated sodium ion channels, the sodium influx starts. So as a sodium is a positively charged ion, it is taken inside the cell, the negative charge which was built up inside the plasma membrane, that starts decreasing. So this increases positive charge inside the cell. Okay, and that is why from the minus 70 or minus 90 millivolt, the membrane potential changes from minus 90 millivolt to some, let's say here, minus 55 millivolt. And when this value crosses certain threshold, here the threshold value is minus 55 millivolt. So when the membrane potential value crosses this threshold, a sudden opening of voltage gated sodium channels is seen. So there will be sudden opening of all voltage gated sodium ion channels. So this results into more and more sodium influx. So as more and more sodium is taken inside the cell, this value, instead of this value, this membrane potential, which was initially the equilibrium potential of potassium ions. So this was the resting membrane potential, right? resting in membrane potential was almost similar to the equilibrium potential of potassium ions because the potassium ions were in equilibrium. But this starts shifting towards more positive side, okay, because the charge separation is reduced. And once this starts shifting to positive side, this reaches somewhat about 40 millivolt, positive 40 millivolt. So this shifts from the equilibrium, the membrane potential, the Vm, which was at rest, which we call resting membrane potential, that was around the equilibrium potential of potassium ion. This shifts from the equilibrium potential of potassium to the equilibrium potential of sodium ions. Okay, but this is not exactly equal. Again, at the rest, the resting membrane potential is not exactly equal to the equilibrium potential of potassium ions. This is similar to the equilibrium potential of potassium ion. I just like that, the membrane potential after sudden depolarization. So after this, the sudden depolarization, when it crosses the certain threshold, it gets equal, it gets similar, it gets closer to the equilibrium potential of sodium ions, which is equal to plus 55 millivolt. So this is around that value, okay? The resting membrane potential, like the membrane potential, Vm reaches around to that value. And when this reaches this value, it is called as action potential because now the action will be generated. Okay, that is why it is known as action potential. So action potential is a sudden and transient change in the membrane potential from the rest when it gets depolarized. Okay. So I hope this is clear. Action potential is somewhat near to the equilibrium potential of sodium ions. But this does not get equal because first of all, there is some potassium efflux. Okay, so why is it not exactly equal? So at the rest, Vm is Vm is similar to equilibrium potential of potassium ions, but it is not exactly equal because there is some sodium influx, right? In the same way, when the action potential is generated, okay, the membrane potential at that time is similar to the equilibrium potential of sodium ions, but it is not exactly equal because there is some potassium efflux. Okay, why is there some potassium efflux? Because see, there is the concentration gradient of the potassium is quite high on the inside. So there, even though there are some voltage gated sodium ion channels open, so the voltage gated sodium ion channels, they are open, so they are going to take sodium from outside to inside. Even the charge separation is decreasing. So it decreases till minus 55 millivolt. Even though it is decreased, but there is still some charge separation, right? And the concentration gradient of potassium ions is high on the inside. So now as there are more potassium ions inside, some potassium ions will leak through that membrane. So some potassium ion will move from inside to outside, so there will be potassium efflux. Okay, so because leak channels, potassium efflux will be due to the potassium ion leak channels, and this will ensure that the membrane potential does not get exactly equal to the equilibrium potential of sodium ions. And then there's some chloride influx as well. Even though the membrane is selectively permeable to potassium ions, but it is somewhat permeable to sodium ions as well as chloride ions. So, voltage gated chloride ions, they will be doing this chloride influx, and that will help us not exactly, so that will result into membrane potential not reaching exactly to the equilibrium potential of sodium ions. Okay, so let's summarize the depolarization state. So the very first thing that happens is that when the stimulus arises, the charge separation is decreased. So how is it decreased? It is decreased by the influx of sodium ions. Voltage gated sodium ion channels open, which increase the sodium ion influx, which increase the depolarization. Okay, so once this the more and more sodium ions are taken in, the more and more voltage gated sodium ion channels will open. This is what we call the positive feedback loop for sodium ions. Okay, so there is a positive feedback loop for sodium ions. What is that loop? See, first a few sodium ions will come in that will open the voltage gated ion channels. Okay, so now voltage gated sodium ion channels are open. So because they are open, they will promote more influx of sodium ions. Now the more and more sodium ions are getting in the inside the cell, more and more voltage gated sodium ion channels will open. So this is what we call positive loop. So few there will be sodium influx, okay, which will open sodium ion channels. And once sodium ion channels are open, they will increase the influx. As the influxes increase, they will increase the opening of the sodium voltage gated sodium ion channels. This is what we call as the positive feedback loop. So I hope the depolarization state of the neurons is clear to you all. At this stage, the action potential is generated. So let's see that, let's take a look at the graphical representation. Okay, so this is the 0 millivolt, right? And this is some negative value, and here is the positive value. Okay, so this is the voltage, and this represents time. So over time, so for the negative, let's say minus 90 millivolt, this value was maintained with the help of the unequal distribution of ions, with the help of the sodium potassium ATPase pump, as well as the ions are impermeable, and that is why this negative resting membrane potential is maintained. So this is the resting membrane potential. This was maintained. So now there's some stimulus. So once the stimulus arises, the sudden so stimulus, okay, let me mention it here. The stimulus should have first enough strength, means the intensity should be enough. Okay, so it should be strong enough to, to spike the action potential, as well as it should last for some duration. Okay, so those two things are quite important for the sudden opening of sodium ion channels, voltage gated sodium ion channels. So once that happens, there will be a certain spike, okay, and then it will reach to this level. So here, let's say this is the 40 millivolt. This is what we call as the action potential. Okay, so once this action potential is reached, now it's like, whenever water is at high potential, it has a tendency to flow towards the lower potential. So this is high potential and this is low potential scenario, and when you join them by a tube, the water will flow from here to here. Okay, so this will be the water movement. It has a tendency to move from higher potential to the lower potential. So now with time, so once the water starts moving from the container A to container B, the 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 water level starts rising in container B, and with time it will get equal to what is there in the container A, right? So with time, let's say the both of the water levels, they get equal. So once they get equal, the driving force, the force which was driving the water to move from higher potential to the lower potential, this decreases, right? This decreases over time. But in neurons, this doesn't happen in this way, because this driving force is maintained due to unequal distribution of ions. right? Why the driving force decreased in this scenario? Because the water level gets equally distributed, right? Water is getting equally distributed. But in the case of neurons, the unequal distribution is maintained through the leaky channels, right? And then it again has impermeability for ions. Let's say if I just put a blocks in this tube. So now water can't move from A to B, and there will be there. So this blockage is, blocking the water movement from container A to container B. So the driving force will always be maintained. So in the same way, the anionic impermeability of the membrane keeps the driving force as it is. And then there is sodium potassium pump sodium potassium ATPase pump, which uses one ATP molecule to maintain this difference. So this is the resting membrane potential scenario. But once this driving force decreases and let's say it reaches to zero, now you have to ensure that this driving force is maintained again, so that when the next stimulus arises, the neuron can get excited, right? The neurons are excitable because that membrane potential, the resting membrane potential, is being maintained. This driving force, or let's say the charge separation, the charge separation is being maintained, and that is why the neurons are excitable. And if you don't, the once they lose this charge separation, they will lose their property of excitability. And that is why the maintenance is quite important. So when it's like whenever electron gets excited and it reaches to the higher energy state, it comes back. Okay, but you have to put that back so that you have so it okay, yeah. It's like, so let me draw it nicely. So like this is the ground state and this is the higher energy level state. Okay, so once you provide energy to this electron, this jumps from the ground level to a higher energy state, and once it reaches to the higher energy state, due to this external force, due to this external energy supply, once it reaches to the higher energy state, eventually it is going to come back. Okay, and that happens in the next scenario. As the potential increases to the positive value, it is going to fall down. Okay, so this is an inevitable thing that is going to happen. But then after that, we have to maintain the driving force, and that is why after depolarization of membrane, once the membrane gets depolarized, okay, from the resting state, it will eventually get repolarized. Okay, so this repolarization happens, and this is a quite natural thing, because it is the nature of the things. Like once you reach to the top, you have to fall back down. You have to come to your resting stage. You have to come to the ground state. So um, in the depolarization, all of the voltage gated sodium ion channels were open, while in the repolarization, voltage gated potassium ion channels open. But unlike sodium ion channels opening, which was sudden and quick, the opening of voltage gated potassium ion channels is rather slow. Okay, so this actually, there's no clear cut, there is no clear cut boundary that at point eight millisecond or whatever, the voltage gated sodium ion channels open. There's no clear cut boundary between those two steps. As soon as the sodium ion, as soon as after resting membrane potential, there is sudden opening of sodium ion channels. Okay, then at this stage, somewhere here, there will be the slow opening of voltage gated potassium ion channels, and that is why the equilibrium, the membrane potential never reaches to the plus 55 value. So let me draw it again. So I'm trying to explain that whenever at the resting stage, there will be stimulus and there will be sudden opening of sodium ion channels, right? And it will reach, so it will reach to plus 40 millivolt value, but it should reach to So it has a potential to reach to the plus 55 millivolt value, because that is the equilibrium potential of sodium ion channels. That much potential the membrane should have, because it has that much concentration of sodium ions, but it never reaches to this value. Why? It stops at the 40 millivolt, because at this point, so somewhere here, like when the membrane potential reaches somewhere here, the voltage gated potassium ion channel starts opening. Though the process is very slow, the opening of potassium ion channels is very slow. They do open at this point, and they starts the efflux of the potassium ion channels. And now, due to the efflux of potassium ion channels, the membrane potential never reaches to 55 millivolt. It just drops down after this point, and this state is known as repolarization. Okay, so in repolarization, the voltage gated potassium ion channels open, which do the potassium efflux. Okay, so this potassium efflux, once this potassium starts getting out of the cell, it does the sodium ion channels inactivation. Okay, so this though whatever sodium ion channels were open during the depolarization state, they get inactivated. So the sodium efflux stops. So sorry, sodium influx stops. So there won't be any sodium coming in. All of the potassium ions will move out. Okay, so this is how the repolarization during the repolarization state, the resting membrane potential is achieved again. But here comes the twist. Once it reaches to some 90 millivolt value, the the membrane potential goes down. It keep going down, and it reaches to certain value like minus 110 millivolt or minus 120 millivolt. It reaches to that certain value, and then it starts rising again, and it is maintained. Why does this happen, and what is this called? So this state is known as hyperpolarization. Means the charge separation which was at the rest stage, that is increased. So during the depolarization, this stage, depolarization, the charge separation is decreased. Okay, and then again starts increasing during the repolarization state. But while increasing, it keeps increasing beyond the resting stage. And so like whatever charge separation was there during the resting stage, after it increases beyond that, so there will be increase in charge separation. That increase in charge separation is known as hyperpolarization of the membrane, hyperpolarization of the neuronal membrane. And why does this happen? This happens because I already told you the opening and closing of voltage gated potassium ion channels is slow. So the way the opening is slow, the potassium ion channels, they close their gate slowly. Okay, so due to this slow inactivation of potassium ion channels, the potassium efflux goes on even after the resting membrane potential is achieved, and it reaches to minus 120 millivolt value. And then now after the hyperpolarization state, once the once the voltage gated ion channels, the the potassium ion channels, they start closing slowly. Once they are closed completely, now the sodium potassium pump opens, which helps us in restoring the resting membrane potential. We have already seen how does it restore the resting membrane potential. It takes it fluxes, like it moves the three sodium ions out of the cell and moves two potassium ions inside the cell. Okay, so this is how the sodium potassium pump, it maintains the resting membrane potential. Okay, let's do a quick revision of what happens in the neuronal membrane. So first, the cell is at rest. Okay, and when cell is at rest, it has negative charge inside and positive charge build up outside. Okay, and in this rest condition, the rest condition, the resting membrane potential, it is maintained due to sodium ion potassium ion leak channels and the sodium potassium pump. Okay, then the stimulus arrives at the site and it results into increase in charge separation, and due to that the action potential is generated. Okay, so charge separation is reduced. Okay, the reduced charge separation generates action potential, okay, which is nearly equal to equilibrium potential of sodium ions. Here the resting membrane potential was nearly equal to the equilibrium potential of potassium ions. It does not reach to that value exactly due to some efflux of potassium ions as well. So this is achieved due to the opening of sodium ions, sodium ion channels, voltage gated sodium ion channels. Okay, then once this value, some positive value is achieved by the cells, then it starts repolarizing. So this is known as depolarization. Okay, so then it starts repolarizing. In the repolarization state, whatever charge separation was reduced, it is the cell starts to regaining its charge separation. So the reduced charge separation starts to increase. Like it's regaining phase. Okay, that is why it is known as repolarization, because at rest the cell is at polarized state. It is not non-polar in nature, it is polarized because it has a charge separation. Well, then then during the repolarization state, the voltage gated sodium potassium ion channels are open, which are going to do the potassium efflux. But here there was sodium influx. I did not write it. Then the potassium efflux results into the reduction of the increasing the charge separation, regaining the charge separation. And during this stage, those potassium sodium ion channels, they gets inactivated. Okay, so now once they are activated, what happens is that the potassium voltage gated potassium ion channels closing slow, and due to that, the cells keeps increasing the charge separation beyond the what was expected from them. So that results into hyperpolarization. Hyperpolarization. So too much charge separation. Okay, and that is due to the slow closure of voltage gated potassium ion channels. Okay, which keeps the potassium efflux on. And once they are closed, once those potassium voltage gated potassium ion channels are closed, now the sodium and potassium ATPase pump starts and it regains the resting membrane potential. Because now, let's take a look at the ion, the distribution of ions across the membrane. So in the rest state, there is higher sodium and chloride outside, higher potassium and anions inside. Okay, once the depolarization happens, the potassium ions, the sodium ion starts moving in. So now there are less sodium ions, but quite a bit of chloride ions on the outside, and there are sodium ions, much more sodium ions compared to the outside. So the concentration of sodium ions is high on inside. Well, there are potassium ions as well, and anions sitting casually there. Okay, and some chloride ions slip through. some chloride ions slip through. So this helps us maintaining this helps us increasing the membrane potential from negative minus, so 90 to minus 40, but it cannot go beyond because some chloride ions come in and some potassium ions leave the cell. But anyways, the major scenario is the influx of sodium ions. Okay, then during the repolarization, what happens is that there are too much, so now the scenario is there are too much sodium ions inside. Okay, but now the potassium efflux starts. So potassium goes out. There will be potassium efflux. Let me write this clearly. Okay, so the potassium ion will move out. Okay, so this will start increasing the potassium ion levels outside the cell. So in during the hyperpolarization state, the distribution of ions will be somewhat like this. The more potassium ions outside and more sodium ions inside. Somewhat chloride ions here and there. Okay, somewhat chloride ions will slip inside the cell, but still the concentration of chloride ion more outside. Okay, still will be more outside, but some of the chloride ion will slip in. And anions, basically the membrane is impermeable to them, so they cannot move. So this will be the scenario during the hyperpolarization, which is exactly opposite to what we have during the cell at rest. Okay, and to regain whatever scenario was there before the arrival of stimulus, the sodium potassium pump starts, which does the which starts taking, which does the efflux of sodium. So three sodium ions will be pumped outside and two potassium ions will be taken inside. Okay, so let's write it here. So two potassium ions will be taken outside. So three sodium ions out and two potassium ions in. And this will help us regaining the resting membrane potential. So this is the whole scenario of how a cell from rest gets depolarized, then repolarized and hyperpolarized, and then gains its form back. So it's like when you are running in a race. Okay, so you start from the you start from the initial line and you keep running. So you have gained your momentum. So you are quite in a momentum, and when you reach the finish line, you will still skid somewhat forward. Like you won't stop exactly at finish line because you have some momentum. You will stop here, and now you have to come back. And so the whole race track is something like this. You have to start from here and go till the finishing point, and then you have to come back here. But instead of following this path, you follow this path. Okay, you start from here, you skid somewhat further and then come back because you are in the momentum. It's just like that from the rest. So it's just like in the cells from the, okay, let me just rough this. Okay, so from the rest you start. Okay, so the cells start from the rest, the resting membrane potential, the membrane potential increases. So then it starts decreasing and it reaches to the, so it should stop here. Look, okay, let's draw this diagrammatically. Okay, so, well, what's happening? My, no. So in the neurons, so at the, when this is, let's say this is minus 90 millivolt, so the cell is at rest, okay, and due to sudden stimulus, the there will be spike in the membrane potential, so it will reach till plus 40, and then now it should come back. So it starts coming back, but now it has a momentum. So like the, in this case, in this scenario, the sodium ion channels, they open suddenly, and that is why there will be sudden spike. But the potassium ion channels, they are very slow in opening and closing, and that is why the membrane potential, instead of reaching here and stopping and regaining, like instead of being graph like this, the membrane potential goes somewhat down, which is what we call as hyperpolarization. Okay, let me show you a standard graph of that. What's that? Yeah, see ya. So this is how the action potential is generated in a cell. So a stimulus arises, which, which increases the membrane potential to some minus 55 millivolt. Once this threshold is crossed, then there will be this sudden opening of sodium voltage gated sodium ion channels. Before that, you have to reach to the minus 55 millivolt, means there should be a stimulus here, which will, which will open the leaky channels. The leaky channel